There is a star in the shoulder of Orion that has been watched more carefully than almost any other object in the night sky. It is not the closest star. It is not the most massive star. It is not the star most likely to affect Earth in any meaningful way. By most practical measures, it is just another point of ancient light in a sky full of ancient light. And yet astronomers have pointed more instruments at it, published more papers about it, stayed awake more nights studying it than almost any other star you could name. It has generated more scientific debate, more public fascination, more genuine uncertainty among professional researchers than objects 1,000 times more exotic. The star is Betelgeuse, and in January of 2026, something was confirmed about it that changes almost everything scientists thought they understood about how it will die. This is not a story about a star about to explode tomorrow. It is not the kind of dramatic, imminent danger story that gets headlines and then fades when nothing happens. It is something more interesting than that. It is the story of how a star that has been studied for centuries turned out to be hiding something for all of that time. Something that was only confirmed when astronomers combined 8 years of painstaking observations and the most powerful space telescope ever built and a companion star so close to Betelgeuse that it was orbiting inside the giant star's own atmosphere. A companion star that nobody knew for certain was there. Until now. And what that companion star is doing to Betelgeuse, and what it means for the eventual death of one of the most famous stars in the sky, is a story that the universe has been holding in reserve in the shoulder of Orion, waiting for us to build instruments sensitive enough to read it. We finally have. Let's go there. First, you need to understand what Betelgeuse actually is. Not the name, not the mythology, not the popular associations. What it actually is physically in terms of the raw numbers that describe it. Betelgeuse is a red supergiant star. It sits in the constellation Orion, marking the hunter's left shoulder when you face him in the sky, about 650 light-years from Earth. In cosmic terms, this is extraordinarily close. Most of the stars you can see with your naked eye are within a few hundred light-years. In a galaxy 100,000 light-years across, containing 400 billion stars, Betelgeuse is practically in our backyard. Its light takes 650 years to reach us. The light arriving at your eyes tonight left Betelgeuse around 1375, approximately 50 years after the Black Death swept through Europe and roughly 100 years before Columbus sailed west from Spain. Whatever Betelgeuse is doing right now, in the actual present moment, you will not know about it for another 650 years. This is already strange enough, but Betelgeuse gets stranger. The Sun is, by most stellar measures, an average star. Its diameter is approximately 1.4 million kilometers. If the Sun were hollow, you could fit about 1 million Earths inside it. This sounds enormous, and by human standards it is. Betelgeuse would swallow the Sun the way the Sun swallows the Earth. If you replaced the Sun with Betelgeuse, placed it at the center of our solar system, its surface would extend to somewhere between the orbits of Jupiter and Saturn. Everything within that radius would be inside the star. Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter itself would all be submerged in the roiling, churning, million-degree outer atmosphere of a red supergiant. The distance from the center of Betelgeuse to its surface, on a typical day, is approximately 700 times the radius of the Sun. On its pulsating peaks, when the star swells, it may reach 1,000 times the Sun's radius or more. Betelgeuse is not a star in the way you intuitively imagine a star. It is a bloated, churning, dimming and brightening, mass-losing, almost incomprehensibly enormous sphere of plasma held together by gravity and slowly losing the battle. It is, by every measure astronomers use, a star near the end of its life. Not near in the sense of imminent by human timescales, but near in the sense that stars like Betelgeuse do not live long by astronomical standards. The Sun will burn for another 5 billion years. Betelgeuse has already burned for about 10 million years, which is roughly its entire expected lifespan. It is in the last stages of its stellar life, burning helium and heavier elements in its core, losing mass through a powerful stellar wind at a rate that would consume the entire mass of the Earth in roughly 10,000 years. It is not long for this universe. And when it goes, it will not go quietly. The death of a star like Betelgeuse is called a core collapse supernova. It is one of the most violent events in the universe, and understanding what one looks like requires understanding what is happening inside Betelgeuse right now. At the center of Betelgeuse, deep inside layers of increasingly heavy elements, the core is burning. Not hydrogen anymore. Betelgeuse burned through its hydrogen long ago. It moved on to helium, then carbon, then neon, then oxygen. Each fuel is less efficient than the last, burns faster, produces less energy per reaction. The star accelerates through its later fuels at increasing speeds. The final fuel is silicon. Silicon fusion produces iron, and iron is the end of the line. Iron is the most stable nucleus in existence. It sits at the bottom of the nuclear binding energy curve. Fusing lighter elements into heavier ones releases energy up to iron. But fusing iron requires energy rather than releasing it. An iron core cannot generate energy through fusion. It simply accumulates. Inside Betelgeuse right now, silicon is burning in a shell around an iron core. The iron core is growing. The silicon fuel is being consumed. When the silicon shell burns through its fuel, the iron core will be left unsupported. No fusion, no energy generation, no outward pressure to resist the pull of gravity. What happens next takes less than a second. The iron core, suddenly unsupported, collapses under its own gravity. It falls inward at a quarter of the speed of light. In less than a second, a core that was the size of Earth compresses to the size of a city. The density reaches the point where atomic nuclei are pressed together, where protons and electrons merge to form neutrons, where the strong nuclear force finally provides enough pressure to halt the collapse. The infalling outer layers, still rushing inward at a quarter of the speed of light, slam into this suddenly rigid neutron core and rebound. The rebound produces a shockwave of almost incomprehensible power. This shockwave blasts outward through the remaining stellar material. When it reaches the surface, it blows the outer layers of the star away into space at velocities of thousands of kilometers per second. The supernova. In the first moments, Betelgeuse will release more energy than the Sun will release in its entire 10 billion year lifetime. Most of this energy will come in the form of neutrinos, tiny particles that interact so weakly with matter that they pass through the star, through the planet, through you without interaction. A flood of neutrinos from Betelgeuse's death will wash through the Earth, through everything on it, and continue into space without most of them interacting with a single atom. The light will follow the neutrinos, but slowly. The shockwave takes hours to reach the surface of the star. When it does, Betelgeuse will brighten to a luminosity comparable to the entire Milky Way galaxy. It will be visible in daylight. It will cast shadows at night. It will be the brightest object in the sky after the moon, visible for weeks or months. And then it will fade. The expanding cloud of debris will cool and thin, glowing for years before becoming the supernova remnant that marks where Betelgeuse used to be. All of this is coming. At some point, the physics is clear. What has not been clear until very recently is exactly when, and exactly how. Because what was discovered in January 2026 changes some of the most fundamental assumptions about Betelgeuse's final years. Let's go back to 2019 because that is where the modern story of Betelgeuse really begins. In late 2019, Betelgeuse dimmed. Not by the small amounts expected from its normal pulsation cycles, but dramatically. By February 2020, it had dropped to roughly 40% of its typical brightness, the lowest level ever recorded in modern observations. It was so noticeably dimmer that amateur astronomers around the world reported it. You could look at Orion and see that something was different. The internet understandably noticed. Articles circulated suggesting Betelgeuse was about to go supernova. Social media was full of speculation. Astronomers were asked about it in interviews, at conferences, by journalists who wanted to know whether the most spectacular astronomical event in human history was about to unfold. The honest answer from most astronomers was, "We do not know." Not because they were being evasive, but because Betelgeuse had never dimmed this dramatically before in the period of modern systematic observation, and they genuinely did not know what it meant. The most conservative explanations: dust clouds ejected from the stellar surface blocking the light, changes in the star's normal pulsation cycles coinciding to produce an unusually deep minimum, were considered likely. But they could not be confirmed immediately, and the more dramatic explanation, that this was the beginning of the end, the first observable sign of the structural changes that precede a core collapse, could not be immediately ruled out. What followed was an extraordinary period of intensive observation. Every telescope that could be pointed at Betelgeuse was pointed at Betelgeuse. Hubble observed it. Ground-based observatories in multiple countries tracked it. Radio telescopes mapped its surface and atmosphere. Infrared instruments looked through the dust that visible light could not penetrate. The conclusion, assembled over months of analysis, was that the 2019 to 2020 Great Dimming, as it came to be called, was caused by a massive ejection of material from the star's surface. A bubble of superhot plasma, roughly 15 times the diameter of the Sun, erupted from the surface of Betelgeuse and traveled outward into the cooler outer atmosphere. As it cooled, it condensed into dust. The dust cloud, between Betelgeuse and Earth, absorbed and scattered the star's light, reducing its apparent brightness. This was not a sign of imminent death. It was a sign of a star doing what red supergiants do: losing mass, ejecting material, slowly shedding itself into the surrounding space as it approaches the final stages of its evolution. Betelgeuse brightened again. By early 2021, it was back to normal. By late 2022, it was brighter than average. By 2023, it was behaving more or less normally, pulsating through its usual cycles. But the questions the Great Dimming had raised did not go away, because the massive ejection that caused it, the scale of that event, the amount of material it released, the energy required to produce it, was not well explained by the models of Betelgeuse that existed at the time. Something else was going on. Something that had been theorized for years, sought for years, and finally confirmed in January of 2026. For decades, there had been hints in the data that Betelgeuse might not be alone. Stellar companions are common in the universe. Most massive stars are found in binary or multiple systems, gravitationally bound pairs or groups of stars orbiting their common center of mass. The Sun is unusual in being a single star. Stars like Betelgeuse, born in the dense molecular clouds where massive star formation occurs, typically form in close proximity to other stars and often end up gravitationally paired with companions. But finding a companion to Betelgeuse had proven extraordinarily difficult. The problem is geometry and scale. Betelgeuse is so enormous, its disk so large in the sky, its atmosphere so extended, that anything in its immediate vicinity would be completely overwhelmed by its light. A companion star, even a substantial one, would be like trying to see a candle held next to a searchlight. The searchlight's glare makes the candle invisible from any practical distance. The only way to find a companion to Betelgeuse is not to look for it directly, but to look for its effects. Its gravitational influence on the motion of material around Betelgeuse. Its effect on the timing of Betelgeuse's pulsations. Its wake as it moves through Betelgeuse's extended outer atmosphere. In 2024, a team of astronomers analyzing long-term radial velocity measurements, precise measurements of how fast Betelgeuse is moving toward or away from Earth at different times, found a periodic signal that was most naturally explained by the gravitational influence of a companion. The period was approximately 2,170 days, a little under 6 years. The signal implied a companion with a mass somewhere in the range of 1 to 2 times the mass of the Sun, orbiting so close to Betelgeuse that it was actually inside the giant star's extended atmosphere. Not beside Betelgeuse, inside it, embedded in the outer layers of gas that extend far beyond the star's visible surface. This was the companion that was subsequently named Siwarha, and the confirmation of its existence in January 2026 using Hubble observations combined with 8 years of multi-wavelength monitoring, changed everything. Let's be precise about what was confirmed. The January 2026 paper from the Center for Astrophysics at Harvard and Smithsonian did not directly image Siwarha. The companion is currently hidden behind Betelgeuse itself from our line of sight, with Betelgeuse eclipsing the companion. It will emerge from behind Betelgeuse in approximately 2027, and astronomers are already planning observations to catch it the moment it becomes accessible. What the paper confirmed was the wake of Siwarha. As the companion star plows through the dense gas of Betelgeuse's extended outer atmosphere, it creates a trail of denser, disturbed material behind it, similar to the wake of a boat moving through water or the bow shock of a spacecraft moving through the thin gas of interplanetary space. By tracking subtle changes in the polarization and absorption of Betelgeuse's light over 8 years, the team was able to detect the periodic signature of this wake. The pattern matched the predicted orbital period. The scale of the disturbance matched the predicted mass of the companion. The geometry was consistent with a star moving through the outer atmosphere of a red supergiant at close range. The evidence, assembled carefully, pointed in one direction. Siwarha is real. Siwarha is there. And Siwarha is doing something that nobody had fully appreciated before its confirmation. It is stirring up Betelgeuse. Not gently, not subtly. It is plowing through the outer atmosphere of the giant star, churning the gas, creating density waves, altering the outflow of material from Betelgeuse's surface, and quite possibly playing a role in producing the kinds of massive ejections that cause the Great Dimming. The discovery does not mean Betelgeuse is about to explode because of Siwarha. It means the dynamics of Betelgeuse's atmosphere, the patterns of mass loss, the timing and scale of ejections, the way the star sheds itself into space in its final millennia, are being driven not just by the internal physics of the star itself, but by the gravitational stirring of a companion embedded within it. This is new, this is significant, and it changes the calculations about what Betelgeuse's death will look like. Here is what has changed and why it matters. The standard model of how a red supergiant evolves toward a supernova treats the star as a single object. Its internal physics, the fusion reactions in its core and shells, the convective currents that carry energy from the core to the surface, the stellar wind that carries mass away into space. All of this is modeled as the behavior of a single star. If Siwarha is real and orbiting within Betelgeuse's atmosphere, the single star model is wrong, or at least incomplete. A companion embedded in the outer atmosphere of a red supergiant adds gravitational perturbations to the flow of material from the star's surface. Every orbit, Siwarha passes through the gas at a slightly different angle, creating a periodic enhancement of the density in specific regions of the atmosphere. These enhancements can trigger larger-scale convective motions. They can produce density waves that travel inward toward the stellar surface and amplify the normal convective currents that carry energy outward. In the most dramatic interpretation, the one that requires the most caution but cannot be dismissed, the gravitational stirring from Siwarha may be responsible for or contributing to the episodes of dramatically enhanced mass loss that Betelgeuse has been showing, including the Great Dimming of 2019 to 2020. If the Great Dimming was caused in part by Siwarha's gravitational influence, if the massive eruption that ejected the dust cloud was triggered or amplified by the companion's orbital dynamics, then Betelgeuse's mass loss is not a random statistical process but a periodic one, tied to Siwarha's orbital period of roughly 2,170 days, predictable in principle from the companion's position. This would mean that the next major mass ejection from Betelgeuse is not random but can be anticipated. Scientists would know when to look. They would know when to prepare their instruments. And crucially, they would have a much better picture of how quickly Betelgeuse is losing mass, because the mass loss events would be systematically enhanced by the companion's passage rather than occurring randomly. The enhanced mass loss changes the estimated timeline of Betelgeuse's evolution. If mass loss is proceeding faster than the single-star models predicted, then Betelgeuse is closer to the conditions required for core collapse than those models suggest. Not by thousands of years, but closer. The uncertainty in Betelgeuse's supernova timing is enormous. The star could go supernova in 100,000 years, or it could go in 10,000, or it could go in 1,000. The models are not precise enough to distinguish between these possibilities. But any systematic enhancement of mass loss shifts the probability distribution toward the shorter end. Betelgeuse, in the light of the Siwarha discovery, may be further along its evolutionary track than scientists thought a year ago. Now let's talk about what Siwarha actually is, because this is one of the more surprising aspects of the discovery. When the companion was first theorized from radial velocity data, astronomers made reasonable guesses about its nature. A star of 1 to 2 solar masses at the age of Betelgeuse's stellar system could be many things. Could be a main sequence star, burning hydrogen normally. It could be a compact remnant, a white dwarf or neutron star, the burned-out core of a star that evolved faster than Betelgeuse and died first. In October 2025, researchers from Carnegie Mellon University published observations that suggested the companion was not a compact remnant. The spectral signature they detected was more consistent with a young, relatively normal star, something closer in size and luminosity to the Sun, still in an active phase of its life rather than a burned-out remnant. This was unexpected. A youngish companion to an ancient, dying supergiant does not fit neatly into standard models of binary star evolution. If both stars formed from the same molecular cloud at roughly the same time, why is one of them, Betelgeuse, so evolved so near the end of its life, while the other appears relatively young? There are several possible explanations. One involves mass transfer. In some binary systems, the more massive star evolves faster and, as it expands in its red giant phase, can transfer mass to its companion. This transferred mass can rejuvenate the companion, giving it fresh hydrogen fuel and effectively resetting part of its evolutionary clock. A companion that has gained mass from Betelgeuse over millions of years might appear younger than its actual age because it is richer in hydrogen than it would otherwise be. Another possibility is that the two stars formed under unusual conditions that are not fully captured by standard models of binary formation, perhaps from material at different points in the molecular cloud, with different initial conditions that led to different evolutionary rates. Whatever the explanation, the nature of Siwarha adds complexity to the system. A main sequence companion embedded in the atmosphere of a red supergiant is not something that has been modeled in detail before. The interaction between the companion's stellar wind, its radiation, and the dense gas of Betelgeuse's outer atmosphere is a problem that theorists are only now beginning to work through. The models will take years to develop. The observations to test those models are being planned. And in 2027, when Betelgeuse's eclipse of its companion ends and Siwarha emerges from behind the giant star, there will be an opportunity to observe the companion directly that has never existed before. What those observations will reveal is, at this point, genuinely unknown. Let's take a step back from the recent discovery and spend some time with what Betelgeuse is actually like, because the scale of this star deserves to be felt, not just noted. You have seen the comparison to the solar system, but let's make it more concrete. Right now, as you lie here, the Earth is roughly 150 million kilometers from the Sun. This distance, 1 astronomical unit, is the baseline for measuring all the distances in the solar system. Mercury is 0.4 astronomical units from the Sun. Neptune is 30 astronomical units. The Voyager probes, the most distant human-made objects, are now more than 150 astronomical units from the Sun. The radius of Betelgeuse on a typical day is approximately 700 to 800 times the radius of the Sun. The Sun's radius is 0.0046 astronomical units. Betelgeuse's radius is therefore approximately 3 to 4 astronomical units. If Betelgeuse were placed at the center of our solar system, its surface would be somewhere between the orbits of Mars and Jupiter. The entire inner solar system would be inside the star. But Betelgeuse's extended atmosphere, the tenuous outer layers of gas that extend far beyond the visible surface, reaches much further. It extends to perhaps 10 to 15 astronomical units. If Betelgeuse were our Sun, its outer atmosphere would encompass Saturn's orbit. Everything interior to Saturn would be submerged in Betelgeuse gas. And Siwarha, the newly confirmed companion, orbits within this atmosphere, at a distance estimated at roughly 2 to 5 astronomical units from Betelgeuse's center, inside the region where the extended atmosphere is dense enough to create a significant wake behind the companion's motion. Siwarha is, in this sense, not a companion star in the conventional sense of two stars separated by empty space. It is a star embedded within another star, moving through the outer layers of gas that belong to Betelgeuse, completing each orbit not through vacuum but through a warm, dense, slowly outflowing stellar wind. The image this creates, a star the size of the Sun, moving through the outer atmosphere of a star large enough to contain the inner solar system, stirring the gas with its passage, creating ripples and wakes and density waves, is unlike anything in the standard models of stellar physics. It is a genuinely new type of system, a genuinely new kind of observation, and the implications of it, worked out fully, will take years of theoretical development to understand. There is something in the Betelgeuse story that is worth pausing on, because it is easy to miss in the details of companion stars and mass ejections and orbital periods. Betelgeuse is so close, 650 light-years, next door by galactic standards, that when it goes supernova, the event will be visible to the naked eye in daylight. This has not happened in recorded history. The last supernova visible to the naked eye was observed in 1987, in the Large Magellanic Cloud, a satellite galaxy of the Milky Way roughly 168,000 light-years away. The last supernova in the Milky Way itself that was visible to the naked eye was observed in 1604 by Johannes Kepler, before the invention of the telescope. A Betelgeuse supernova at 650 light-years would be orders of magnitude closer and orders of magnitude brighter than either of these events. Estimates of its peak brightness range from comparable to the full moon to perhaps brighter, depending on exactly how the explosion proceeds and how the light curves with the dust environment around the star. At peak brightness, it would be visible in full daylight. At night, it would cast shadows. This will happen. At some point, Betelgeuse will go supernova. The question is only when. And the when, for the people who will be alive to see it, matters enormously. Because a Betelgeuse supernova will be the most spectacular astronomical event in recorded human history. More dramatic than the 1054 supernova that created the Crab Nebula, visible in daylight for 23 days according to Chinese astronomers. More dramatic than any comet or eclipse or conjunction. A new star in Orion, bright enough to cast shadows, visible for weeks or months, slowly fading into a glowing remnant that will be visible for years. Every telescope on Earth and in space will be pointed at it. Every neutrino detector will catch the flood of particles that arrives hours before the light. Every gravitational wave detector will be listening for the spacetime ripples produced by the asymmetric collapse. The data harvest from a Betelgeuse supernova will exceed everything previously collected from supernova observations by multiple orders of magnitude. It will answer questions about core collapse physics that have been open for decades. It will test neutrino physics models that cannot be tested in any laboratory. It will provide the most detailed picture of stellar death ever obtained. Whenever it happens, let's talk about the neutrino signal, because it is one of the most extraordinary things about a nearby supernova, and it is rarely explained in full. Neutrinos are produced in enormous quantities during a core collapse supernova. Most of the energy released in the collapse, more than 99% of it, comes out as neutrinos rather than light. The light of the supernova, spectacular as it is a tiny fraction of the total energy budget. In 1987, when the supernova in the Large Magellanic Cloud went off, 3 neutrino detectors around the world, in Japan, in Ohio, and in Russia, detected a burst of neutrinos approximately 3 hours before the light from the supernova arrived. Those detectors, which were not designed specifically to catch supernova neutrinos, recorded a total of 25 neutrino interactions in the span of about 13 seconds. 25, from an event that released 10 to the power of 58 neutrinos. The number of neutrinos that passed through the Earth in those 13 seconds from the 1987 supernova is essentially uncountable by human intuition. Every square centimeter of the Earth's surface was crossed by hundreds of billions of them. Most passed through the entire planet without interacting with a single atom. The 25 that were detected were the extraordinarily rare ones that happened to interact with the detector material. Betelgeuse is 400 times closer than the 1987 supernova. Neutrino flux scales with the inverse square of the distance. A star 400 times closer produces, at our location 400 squared, 160,000 times more neutrino flux. The neutrino detectors operating today are also enormously more sensitive than those operating in 1987. Super Kamiokande in Japan, with its 50,000 tons of ultrapure water, is many times more sensitive than its predecessors. Its successor, Hyper Kamiokande, currently under construction, will be even larger. When Betelgeuse goes supernova, Super Kamiokande will detect not 25 neutrino interactions, but something like 10,000 in the first few seconds. The data coming in will be a flood of information about conditions inside the collapsing core at the moment of its death. And because the neutrinos arrive before the light, the core collapses and releases its neutrino burst, but the shockwave takes hours to reach the surface and produce the optical brightening. The neutrino detectors will give several hours of warning. Astronomers will know Betelgeuse is going supernova before they can see it. Automatic alerts will be sent to every major telescope in the world. Observatories will slew to Orion. The full array of human observational infrastructure will be pointed and ready before the first photon of the supernova reaches Earth's atmosphere. This is an extraordinary situation with no precedent in astronomical history. A known star close enough to produce a detectable supernova, monitored continuously with multiple early warning systems in place. The preparation for this event, though uncertain in timing, is already underway. The discovery of Siwarha adds a new dimension to the preparation. If the companion's orbit is well characterized, and the 2026 paper provides a much better characterization than previously existed, then astronomers can predict with some accuracy where in its orbit Siwarha will be at any given time. They can predict when the companion will be on the near side of Betelgeuse, when it will create the most disturbance in the atmosphere, when the enhanced mass loss effects should be most pronounced. If there is any systematic relationship between Siwarha's orbital phase and the timing of major mass ejections from Betelgeuse, and the evidence is consistent with such a relationship, though not yet definitive, then the major ejection events can be anticipated. The next great dimming, if there is one, might be predictable. This is a completely new capability. Before Siwarha, mass loss events from Betelgeuse were treated as statistically random. They happened when internal convective processes happened to align in the right way, and no external clock predicted them. If Siwarha's orbital period provides such a clock, the entire picture of Betelgeuse's evolution changes from a stochastic process to a partially deterministic one. Partially, not fully. The internal convective processes are still chaotic and unpredictable in detail. The companion's gravity provides a periodic perturbation, but the response of the stellar atmosphere to that perturbation is not simple or linear. The system is complex enough that precise prediction of individual events is not realistic. But the knowledge that there is a clock, that every 2,170 days, Siwarha completes another orbit and perturbs the atmosphere in a specific way, changes the prior probabilities. It changes what astronomers look for, when they look for it, and how they interpret what they see. Now let's go to what a Betelgeuse supernova with a known companion actually looks like. A standard core collapse supernova proceeds roughly as described earlier. The iron core collapses. The shockwave blows the outer layers outward. The star brightens dramatically, fades over months, and leaves a neutron star or black hole at the center surrounded by an expanding cloud of debris. A core collapse supernova in a binary system, and specifically a core collapse supernova where one member of the binary is embedded inside the other, is something considerably more complicated. When Betelgeuse collapses, the energy released in the explosion is asymmetric. The shockwave does not travel outward uniformly in all directions. The presence of Siwarha in the outer atmosphere creates asymmetry in the density distribution of gas around Betelgeuse. The side with the companion has denser gas. The side without it has less. The shockwave, moving through this non-uniform medium, will accelerate faster in the lower density direction and slower in the higher density direction. The result is an aspherical explosion, not a perfect sphere of expanding gas, but an elongated or asymmetric cloud of debris. The direction of elongation will reflect the position of Siwarha at the moment of collapse. The fate of Siwarha itself during the explosion depends on several factors that are difficult to calculate without more detailed models. In some binary supernova scenarios, the explosion provides enough energy to the companion, through radiation and direct impact of the shockwave, to unbind it from the system. The companion, suddenly freed from the gravity of the dead star, flies off into space at whatever velocity it had in its orbit at the moment of the explosion. In other scenarios, the companion is retained. If the neutron star or black hole left by the supernova is massive enough, and if the explosion is not perfectly symmetric, the two objects may remain gravitationally bound and become a binary system composed of a neutron star and a main sequence star. Such systems are known. There are several confirmed examples in the Milky Way, including the famous Hulse-Taylor binary pulsar, and they are among the most exotic objects in the galaxy. In Betelgeuse's case, the current mass estimates for Siwarha and the predicted dynamics of the explosion make both outcomes possible. Whether Siwarha survives as a companion to the Betelgeuse remnant or is flung free into interstellar space is something that theorists are working to calculate now that the companion's properties are better constrained. The answer will probably not be known until the supernova itself provides the definitive observational test. Let's talk about what happens to the region of sky where Betelgeuse is now, in the centuries and millennia after the supernova. The expanding cloud of debris from the supernova remnant, will grow. In the first hours, it is still inside what was Betelgeuse's atmosphere. In the first years, it expands outward into the surrounding space, sweeping up the gas that was lost from Betelgeuse over its long lifetime of enhanced mass loss. In the first centuries, it becomes a glowing nebula, a shell of hot gas and dust expanding at thousands of kilometers per second. The remnant of Betelgeuse, in time, will join the gallery of supernova remnants that mark the locations of dead stars. The Crab Nebula, product of the 1054 supernova, is 6,500 light-years away and has been expanding for nearly 1,000 years. It is now roughly 11 light-years across and still growing. At 650 light-years, much closer than the Crab, the Betelgeuse remnant will eventually be an enormous structure on the sky. Not immediately. In the first centuries after the explosion, it will be a point of fading light as the initial brightness decays. But over hundreds of years, as the expanding shell sweeps up material and interacts with the stellar wind that Betelgeuse has been ejecting for thousands of years, it will begin to glow as a nebula. The Siwarha companion, if it is flung free from the system, will become a runaway star, a star moving through the galaxy at the relatively high velocity imparted by the explosion. Runaway stars from binary supernova events are known. They have been detected as stars moving at unusual velocities through the galaxy, their trajectories traced back to the locations of supernova remnants. At 650 light-years, the entire drama of the Betelgeuse explosion and its aftermath will be observable in detail that no previous supernova has allowed. Every stage of the remnant's evolution, every phase of the companion's trajectory if it is freed, every pulsation of the neutron star left at the center. It will be the most comprehensively observed supernova in history. Every aspect of what we now theorize about these events will be tested. And some of those theories will almost certainly be wrong. That is how science works. And a Betelgeuse supernova will be the most important test of stellar physics in the history of the discipline. Let's come back to the immediate present. To Betelgeuse as it is right now, sitting in the shoulder of Orion, shining its red light toward Earth with a delay of 650 years. What is Betelgeuse doing right now? In the actual present, not the 650 years ago past we can observe. We do not know. We cannot know. The light arriving tonight left the star in 1375. Whatever is happening there in 2026 will not reach us until 2676. But we can calculate probabilities. We can use what we know about Betelgeuse's evolutionary state, its mass loss rate, its internal structure, the perturbations from Siwarha, and the models of how massive stars evolve, and we can estimate where in its life cycle Betelgeuse probably is right now. The estimates are uncertain and hotly debated. Some models suggest Betelgeuse has between 10,000 and 100,000 years before core collapse. Others suggest the timeline could be shorter, perhaps as short as a few thousand years, if the enhanced mass loss from Siwarha's stirring has been proceeding at the rates implied by the recent observations. A few thousand years sounds long, and by human timescales, it is. No one alive today, no one's great-grandchildren, probably no one in any civilization that could be called continuous with ours, will see Betelgeuse explode if the estimate is thousands of years. But by astronomical standards, a few thousand years is nothing. It is a rounding error in the lifespan of a galaxy. It means that by astronomical measures, Betelgeuse is on the very edge of its final phase. And there is a non-zero probability, small but real and somewhat larger than scientists estimated before Siwarha was confirmed, that Betelgeuse's death is closer than the most conservative models suggest. That the combination of Siwarha's orbital dynamics and the enhanced mass loss they produce has accelerated Betelgeuse's evolution toward the final collapse. Not imminent by human standards, but closer than we thought. Now let's zoom out, because Betelgeuse exists in a context, a galaxy, a cosmic web, a universe, that gives its story a deeper meaning than the details of companion stars and supernova timelines alone can provide. Betelgeuse was formed roughly 10 million years ago in a region of intense star formation. The molecular cloud that gave birth to it has long since dispersed, its gas consumed by the formation of many stars, most of them less massive than Betelgeuse and therefore still burning today. Betelgeuse itself is one of the rare massive stars that form from such clouds, rare because massive stars consume their fuel quickly and die young, leaving behind the abundant low-mass stars that will still be burning long after all the Betelgeuses in the galaxy have gone supernova. The atoms that make up Betelgeuse were assembled in previous generations of stars. The iron at its core, the oxygen in its outer layers, the carbon and nitrogen and silicon, all of these heavier elements were created in the nuclear furnaces of stars that lived and died before Betelgeuse was born. Stellar nucleosynthesis, the creation of heavy elements in stellar interiors, is how the universe builds its periodic table. Each generation of massive stars creates heavier elements, which are scattered by supernovae, which become the raw material for the next generation. Betelgeuse itself is a product of this process. When it goes supernova, it will scatter the elements it has forged, iron, silicon, oxygen, neon, and the heavier elements synthesized in the explosion itself, into the surrounding interstellar medium. Those elements will drift through space for millions of years before gravity gathers them into a new molecular cloud, where they will form new stars and new planetary systems. The atoms from Betelgeuse will become parts of planets, parts of oceans and atmospheres, parts of living things if the right conditions arise. The carbon in some future creature's DNA may carry atoms that were forged in the core of Betelgeuse and scattered by its supernova. This is not metaphor. This is chemistry. This is how the universe works. We are already made of atoms forged in stars that preceded the sun. The iron in your blood was made in a star that died before the solar system formed. The oxygen in your lungs was made in a stellar core and scattered by a supernova. You are, in a direct and literal sense, the ash of ancient stellar explosions. Betelgeuse will add to that ash. Its contribution to the cosmic inventory of heavy elements will scatter into the galaxy and eventually find its way into new structures. The Betelgeuse supernova, when it comes, is not just a spectacular light show. It is a chemical event, an alchemical event, the transformation of the nuclear fuel stored over 10 million years of stellar burning into the raw materials of everything that will ever be built from it. Let's talk about what Siwarha's existence means for the universe more broadly. Because Betelgeuse and Siwarha are probably not unusual. They are probably representative of a class of objects that is more common than previously recognized. If a massive star can evolve to the red supergiant phase while harboring a companion embedded in its extended atmosphere, If this configuration is stable enough to persist for the millions of years of the supergiant's lifetime, then many of the giant stars we observe as apparently single objects may actually be binary or multiple systems with companions hidden within their atmospheres. The methods used to detect Siwarha, radial velocity monitoring over many years, combined with detailed analysis of spectral line profiles and polarization, can in principle be applied to other massive stars. The search is already underway, with several groups applying similar techniques to other red supergiants in the Milky Way. If companions embedded in stellar atmospheres turn out to be common, the entire catalog of red supergiant observations needs to be reinterpreted. The mass loss rates, pulsation periods, spectral characteristics, and variability patterns of many stars may be influenced by hidden companions that have not been accounted for in the models. This would not make the existing observations wrong. It would make them incomplete. And the correction, understanding which observed features are intrinsic to the star and which are driven by an embedded companion, would require revisiting decades of data with new eyes. Science does this periodically. A new discovery reveals that a class of observations has been systematically misinterpreted, and the entire field reorients to correct the record. The discovery of dark matter required such a reorientation. The discovery of dark energy required such a reorientation. The discovery of the cosmic microwave background required such a reorientation. The discovery of Siwarha and the broader implication that embedded companions may be common in red supergiants may require a more modest but still significant reorientation of stellar astrophysics. Not a revolution, but a substantial correction to models that had not fully accounted for the binary nature of massive stars. There is something in the story of Betelgeuse and Siwarha that is worth sitting with for a moment, separate from the physics and the timelines and the observational programs. We have been watching Betelgeuse for centuries. Ancient Egyptians recorded variable stars, and Betelgeuse's variability is pronounced enough that careful naked eye observers noticed it. Medieval Arab astronomers named it. The name Betelgeuse derives from Arabic, referring to the giant's shoulder. European astronomers tracked it through telescopes from the 17th century onward. Modern spectroscopy, radio astronomy, infrared imaging, and space-based ultraviolet observation have all been applied to it. Centuries of observation, generations of astronomers, instruments of increasing sophistication all pointed at the same point of reddish light in Orion's shoulder. And for all of that time, Betelgeuse had a companion that nobody knew for certain was there, a star orbiting within its atmosphere, stirring its gas, shaping its behavior, contributing to the episodes of mass loss and dimming that have made Betelgeuse one of the most observed and most discussed stars in history. The companion was not hidden by any clever mechanism. It was not deliberately obscured. It was simply small compared to Betelgeuse, and our instruments were not sensitive enough to detect its subtle influence until 8 years of careful monitoring and the precision of Hubble combined to reveal the wake it leaves in Betelgeuse's gas. This is a story about the limits of observation and how those limits are not permanent. Every generation of instruments reveals something that the previous generation could not see. Every increase in precision opens a new window on reality. Every improvement in sensitivity reveals something that was always there, always operating, always shaping what we observed, just below the threshold of what we could detect. What else is below our current threshold? What companions are hidden in other stars we watch? What companions are embedded in systems we believe to be single? What periodicities in the data of other stars are waiting to be recognized as the signatures of hidden objects orbiting within their atmospheres? These are not rhetorical questions. They are research programs, and they are driven by the Betelgeuse discovery, which has demonstrated that the universe contains configurations of matter that our models did not fully anticipate. This is science at its most exciting, not the confirmation of what was expected, the discovery of what was not. Let's end with the star itself. With Betelgeuse as you can see it tonight, or imagine it on a clear night, that red, slightly unsteady point of light marking the hunter's left shoulder in Orion. That light left the star in 1375. It has been traveling for 650 years at the speed of light to reach your eye. It carries information about what Betelgeuse was doing in 1375, but nothing about what it is doing now. What it was doing in 1375 was what it is always doing: burning, pulsating, losing mass to space, shedding itself slowly into the surrounding galaxy, building up the cloud of ejected material that will become the medium through which the supernova shockwave will one day travel. And in 1375, Siwarha was there too, orbiting within the outer atmosphere, stirring the gas, creating its wake, shaping the mass loss in ways that would not be understood for 6.5 centuries. Betelgeuse is not a simple point of light. It is a system, a complex, interacting, evolving system of two stars, one enormous and dying, one smaller and embedded within the dying one's atmosphere, evolving together toward an end that will produce one of the most spectacular events in the history of human skywatching. Whether that event happens in 1,000 years or 100,000 years, it is coming. The physics is clear. The timeline is uncertain but bounded. And the preparation, the neutrino detectors, the telescopes, the theoretical models, the observational program studying Siwarha is already underway. When the light arrives, it will find us ready. And whatever it reveals about the final death of a star it has been watching for centuries, it will find us, as always, willing to revise what we thought we knew in the light of what we actually observe. That is what astronomy has always done. That is what the Betelgeuse story, from its first dimming in 2019 to the confirmation of Siwarha in 2026, continues to demonstrate. The universe is more complex than the models. The models get better. The universe reveals more complexity. And the conversation between the observer and the observed continues, across light years and centuries, with patience and precision and the slow accumulation of understanding. Look up at Orion tonight. Find the red star in the shoulder. The light reaching your eyes left it in 1375. Whatever is happening there right now in 2026, you will not know for 650 years. But you can know this: it is not simple. It never was. And the story it has been telling us across centuries of observation is far from over. Sleep well. For those still awake as the boundary between waking and sleep continues to dissolve. My biggest goal on this channel is to reach to 1,000 subscribers. If you enjoy falling asleep to my videos, please hit that subscribe button. We continue. There is a kind of patience that astronomy teaches that no other discipline quite manages. The patience of light years. The patience of waiting 650 years for information that left its source before any living person's great-great-grandparents were born. The patience of watching a star for 8 years to detect the subtle signature of a companion moving through its atmosphere. The patience of building neutrino detectors and leaving them running for decades, waiting for the burst of particles that will arrive from Betelgeuse's death at some unknown point in the future. Astronomy is full of this patience. And the thing about it, the thing that makes it different from simply waiting, is that the waiting is active. The instruments keep running. The data keeps accumulating. The analysis never stops. The models keep improving. The observations keep refining. The universe does not give up its secrets quickly, but it does give them up, slowly, incrementally, to the instruments and minds that are patient enough to look carefully for long enough. Siwarha was always there, moving through Betelgeuse's atmosphere, stirring the gas, leaving its wake in the data. It was always detectable in principle, just not with the instruments that existed before recently, not with the 8 years of monitoring that was required to see the periodic pattern clearly. Now it is found. Now it is named. Now it is being understood. And it has immediately led to new questions. What exactly is Siwarha? How old is it? How has it evolved in the environment of Betelgeuse's atmosphere? What will happen to it when Betelgeuse collapses? Will it survive the supernova? Will it be flung free into the galaxy? Will it orbit the neutron star remnant for billions of years? These questions will be answered, some of them by observations that are being planned now. the 2027 emergence of Siwarha from behind Betelgeuse, the continued monitoring of the orbital dynamics, the theoretical models being developed to understand the system's evolution. And when Betelgeuse finally goes supernova, whenever that is, every question about Siwarha will receive a definitive answer from the most spectacular natural experiment ever accessible to human astronomy. The patient observation will be rewarded. It always is. Outside, if you can imagine it, Orion is turning slowly with the rest of the sky. The red shoulder is there, sending its ancient light downward through the atmosphere. The photons arriving this moment left Betelgeuse in 1375, carrying information about a star that did not know we were watching and would not have cared. But we are watching. We have been watching for centuries, and we are finally beginning to understand what we have been seeing. Sleep well.